okay? So last time we were talking about the Wittig reaction, right? What does the Wittig reaction do for me? Ultimately, it makes carbon-carbon double bonds from what? Okay, so from aldehydes and ketones plus what? What else do I need? What is it? It is a Wittig reagent, that's true. But what else is it? What else do we call it? Started with a Y. Ylid. It's an ylid, right? So an ylid plus an aldehyde or a ketone will give me a carbon-carbon double bond. And we finished off by talking about how we can make ylids. So we finished last time by talking about the fact that we can take triphenylphosphine, a primary alkyl halide. We can make what's known as a phosphonium salt through an SN2 reaction. I told you this was the easiest reaction in the world to do, and in fact it is. But this is not an ylid. What is an ylid? All right, so it has a positive charge and a negative charge right next to one another. It's like a zwitterion, right? And so we've got to get a negative charge in here, right, on this carbon. And the way that we do that, of course, is by using a base. Now, the base can be strong or, somewhat strong. In this case, they're using butyl lithium. It's a common base that's used for this. Very strong base in this case. Abstracts the proton. You end up with the ylid. You've got the positive and the negative charge. Which one of these species, the phosphorus or the carbon, behave as the nucleophile? The carbon. And why? It's got a negative charge. That's right. And so what do you think is going to happen when we throw this in with a carbonyl? What's going to happen? What's going to be the first step of that reaction? It'll attack the carbonyl carbon and break the weak pi bond. Are you seeing a theme? Right? Carbonyls, we throw them in with nucleophiles, we break the carbon-oxygen pi bond, right? And so it's just a different nucleophile here, right? So let me give you a quick little concepts test. How could we take this and convert it to this? What do we need? I need a Wittig reagent. And I also need a what? Okay, and I also need a what? What's the other reacting partner going to be? Actually, if I have a Wittig reagent itself, I don't need a base. I've already got the Wittig reagent. Would I have to make the ester? This is what I told you had to start with. You can have anything else you want.
So it just has to have the carbon-oxygen double bond?
Where am I going to get that? Not for the carbonyl. This already has a carbonyl, right?
Yeah.
But it's an ester. Notice my product already has an ester in it, right? So this is just one reacting partner. What's the other reacting partner that I need? How do I know what other reacting partner I need? If I look at the product, what else do I need? I need something with a benzene ring, and what else? A carbon chain? What does the Wittig reagent, or what does the Wittig reaction, I should say, give me?
Well, it would give you a carbon-carbon double bond.
It gives me a carbon-carbon double bond. Where's that at? That's right there. So that's where I start thinking about this. And I think about it backwards, right? So I know that the Wittig reaction makes this carbon-carbon double bond. So I can imagine cutting this carbon-carbon double bond in half, and part of this molecule is going to be an aldehyde or a ketone, and the other part's going to come from the Wittig reagent, right? Okay, which part? This part or this part is going to come from the Wittig reagent? The part on the right or the part on the left? This is going to be my Wittig reagent? Okay, look at my starting material. What can I do with this? This I can make a Wittig reagent out of, right? Why? Because it's a primary alkyl halide, right? So I can make the Wittig reagent out of this. This has to be my carbonyl component. What carbonyl do I need, an aldehyde or a ketone? I need an aldehyde. How do you know that? There's only one. So if I look at this carbon, that had to be the carbonyl carbon. It's got a hydrogen attached to it and an aromatic ring, so it has to be an aldehyde. So what I need, right, is I need this aldehyde and I need this Wittig reagent. Right? Now how do I get this Wittig reagent from that? What do I do? What's my first step? What am I going to react it with? What do I need here? Not immediately, but I need a carbon-phosphorus bond, right? For sure. So what am I going to react it with? What's pH mean? It's a phenyl group, so I need PPH3. What is that? Triphenylphosphine. I do the SN2 chemistry. I get the Wittig salt, as we call them, or the phosphonium salts. Now what do I have to do? Now I have to use a base, right? And I can get my ylid out of that reaction, right? By deprotonation. What base could I use here? I could use butyl lithium. That's overkill here. It would work, I'll give you that. If you did it on a test, I'd give you credit for it. But butyl lithium can also react with esters, so I'd have to be very careful about the equivalents that I add, right? And that makes it a little more difficult. I could use NaNH2. That would work, but that too is a little overkill here. What do you know about these protons? Are they more or less acidic than if this was just an alkyl group? Why? Well, but if this was just an alkyl group, you'd still have a positive charge on phosphorus. But why are these hydrogens more acidic than if this was just an R group? What do we know about the carbonyl? Is it electron withdrawing or electron donating? The carbon. Is it electron rich or electron poor? It's electron poor. It's attached to it's got 3 oxygen bonds, right? 2 oxygens, but 3 bonds to oxygen. So that's going to have a partial positive charge, right? Is that going to make those hydrogens more acidic or less acidic? More, right? Because if I have a negative charge next to something that's positively charged and something that's partially positively charged, that's going to stabilize that negative charge, right? It's going to stabilize that anion. Turns out we can get away with a much weaker base here. You can actually use alkoxides. In this case, I would use sodium ethoxide because even if it reacted with the ester, I'd still get the ester back. So I can use a really weak base to do this here because this is activated because of the carbonyl. I would then take my ylid. I would take the benzaldehyde. You would know that you have benzaldehyde because it smells like maraschino cherries. Okay? Because guess what? They have benzaldehyde in them. You would mix it with the ylid. You would stir it around, and lo and behold, you would get that carbon-carbon double bond. This particular product is called a cinnamate. Okay? So when you have an aromatic ring, conjugated double bond to an ester or an acid, these are called cinnamates, and they come from cinnamon, and they smell like cinnamon. Okay? They're esters of cinnamic acid. The mechanism for the Wittig reaction is pretty straightforward. We've already established that we're going to have the carbon function as a nucleophile, break the weak pi bond. That makes our carbon-carbon bond. But that's a sigma bond. That's not a pi bond. How do we get the pi bond? Well, it turns out that phosphorus is highly oxophilic, and it reacts to form what's called an oxophosphatane. Big word. All you need to know is it's a four-membered ring with an oxygen-phosphorus bond. Okay? And this readily eliminates by pushing these arrows to give me a carbon-carbon double bond and a phosphorus-oxygen double bond. What's the driving force for that, do you think? Notice it's not written as an equilibrium. It goes completely to the right. Okay, it doesn't like that. That's true. What else? I could argue that if that was the sole answer, that it would just revert back to starting materials as well. Right? But it doesn't. It goes all the way to product. It is. It's among the strongest bonds we know. How do you intuitively know that to be true? What in biology, for those of you who are in biology, relies on phosphorus-oxygen bonds? ATP is one example. What's another one? DNA. What holds our DNA together? Phosphorus-oxygen bonds. Kind of cool, right? Nature picks one of the most stable bonds to hold our genetic code together. Kind of makes sense, doesn't it? Right? So we know the fact that we're getting this phosphorus-oxygen bond that's really strong. And where do reactions lie? Towards stronger bonds or weaker bonds? Towards stronger bonds, right? And so we've got a weak pi bond. We form this strained system, and we get this really strong phosphorus-oxygen bond at the end that drives the reaction completely to the right. The only problem with this reaction is a sweet reaction to do. The only problem is you generate a lot of mass and waste. Okay? This exact reaction right here I did over and over again when I was a postdoc because we used these for other things, and it was a heck of a lot easier for me to make them than it was to wait on Aldrich to ship them to me. I just sat there and set up 4 or 5 flasks a day, put all the reagents in, let them stir, go to lunch, come back, work them up, take on to the next chemistry that I needed to do. It never failed me, ever. It's that good of a reaction, okay? It's a cool reaction to do. But it generates a lot of waste. And there are people who are studying ways in which you can take the phosphorus-oxygen double bond and recycle it and try to make this a catalytic cycle. The problem that they're having with this is that the phosphorus-oxygen bond is really strong, right? Kind of difficult to do. Nobody's been able to do it effectively yet, okay? But that would really be cool if we could do it, right? Because then we would be able to utilize this reaction on a serious industrial scale, whereas now it's really limited, in my opinion, largely to laboratory and small pilot scale type production because of the waste that gets generated. Okay? Now it turns out that the Wittig reaction has another drawback, and that is that you don't get a single isomer out. Remember when we have double bonds, we can have cis and we can have trans, or E and Z, right? It turns out that if you take an aldehyde like this, you take a phosphorus ylide like this that just has an alkyl group on it, you get about, that's almost 1-to-1, right? I mean, if we fudge the math a little bit, right, which is what I like to do because I'm an organic chemist, right? But 60-40, that's not something that you want to hang on the refrigerator, right? Or that you want to talk to your grandma about, right? It's not great. So why did I do it all the time when I was a postdoc? Because it turns out that if you have a carbonyl group here instead of just an R group, you get almost exclusively trans. It's called a stabilized ylide, and they form the more stable isomer very, very effectively. But if you have just a normal alkyl group, you get this mixture. Now that's okay if you want the mixture. It's not okay if all you want is the E isomer, because all we're going to get is about 60% yield. That'll get you fired in industry, right? But a lot of times people use this reaction because what they're really interested in is making the carbon-carbon bond, not what type of isomer they get, which was another thing that I was interested in as a postdoc, because it really didn't matter to me because I was going to take the double bond and do other chemistry with it anyway and get rid of the carbon-carbon double bond. And so it didn't really matter. But if we have these so-called stabilized ylids, this is a stabilized ylid because we have all this conjugation. We have this aldehyde, which is stabilized because of all this conjugation. We can take this aldehyde, we can take this ylid, we can mix them together, and lo and behold, we can make beta-carotene. Mother Nature doesn't do it this way, but we can do it this way in the laboratory. We can take this aldehyde, this ylid, and we can make that carbon-carbon double bond right there. The cool thing about this reaction is right where that carbon-oxygen double bond is, that's exactly where your carbon-carbon bond is going to be. Always. I know where my carbon-carbon double bond is going to be because I'm doing Wittig chemistry. And so this is colorless. This is color, that's slightly yellow. Mix them together and I get deep orange, right? Because beta-carotene, as we know, is deep orange, if those of us who eat carrots. And this is a very vital, important part of your diet because it is a vitamin A precursor and you need your vitamin A. Eat your carrots, you can see better, all that kind of stuff, right? Doesn't give you x-ray vision or anything like that, but you get, it is good for your eyesight. And we'll talk a little bit about why that's the case today as well. Now suppose you came in to my lab a week ago and I told you to make this carbon-carbon double bond starting from cyclohexanone. How would you have attempted to do this, not knowing the Wittig reaction yet? How might you have attempted to do this? What chemistry do you have in your toolbox that could have done this? Okay, I probably wouldn't reduce it to an alcohol with a hydride reagent, but I might use something else to convert it into an alcohol, what that might be. Because what do I have to get? I have to get a carbon-carbon bond, right? How else do we know to get carbon-carbon bonds from Grignard's or lithium reagents, right? So I wouldn't use a hydride and reduce it, but I would convert it to an alcohol, so you were on the right track, right? So you would have come in and you would have said, okay, Dr. Masterson, perfectly good idea here. We'll just take methyl magnesium bromide. It's cheap. We'll add it. We'll then quench it with water. We'll get the tertiary alcohol because we know that ketones plus Grignards give tertiary alcohols. And then just like Ian said, well, heck, all we have to do is eliminate water and we get the carbon-carbon double bond. But there's this little guy's name that keeps popping up here, Zaitsev's rule, right? He starts to play with us here. And it turns out that under the elimination, this is going to be the minor product. Why is that? Okay, remember it's about alkene stability, right? And so Zaitsev's rule said that we eliminate the hydrogen from the carbon with the, well, it would give us the most substituted alkene, that's true, but the least amount of hydrogens, that's right. So in this mechanism, remember what happens is we'll protonate the alcohol, that will leave and give us a carbocation because this is going to be an E1 elimination, right? We'll have the carbocation, and then we can either eliminate from this beta carbon, or this beta carbon. And these being identical, doesn't matter which one of those has the fewest hydrogens? The methylenes, right? Not the methyl. And so this would be our major product. Conservatively saying, because I haven't actually done this particular experiment myself, you're probably looking at 95% this alkene, 5% this. And if this is the one I wanted you to make, I'm going to give you an F in class and I'm going to send you on your way because 5% isn't the passing grade, right? But what we'll do is now, since you've had the Wittig chemistry, you can fix that problem, can't you? And so what you do is you don't do Grignard chemistry and elimination. You do a simple reaction between cyclohexanone and this very cheap and readily available ylid. And guess what you get as the only product? The carbon-carbon bond exactly where you need it. That's why you need this tool. Okay? And so, because I know that the carbon-carbon bond is going to be formed exactly where that carbon-oxygen bond was, Zaitsev's rule doesn't come into play anymore. Okay? And so that's the power that you really have for the Wittig reaction, other than the fact that I can work with this in air. I don't have to worry so much about moisture. A little bit, not too much. This, can't get it around water. Got to do it under an inert atmosphere to keep the water out. Then I got to isolate this. Then I got to go get the concentrated sulfuric acid. Then I get this, and then I'm going to have to separate the two products, and I'm only going to get about 5% of the one that I want. And I'm going to get an F in the lab, okay? Or I can simply take the cyclohexanone, the triphenylphosphine, or excuse me, the ylid, mix them together in hexane, let them stir, go to lunch, come back, have the product I want, and get an A. You pick, right? Pretty simple. So the Wittig reaction gives me the carbon-carbon double bond exactly where I want it in that particular case. We can also add amines to carbonyl compounds. So an amine will react with aldehydes and ketones to give what are known as imines, okay? And just a quick refresher, we know what a primary amine is, we know what a secondary amine is, and we know what a tertiary amine is, right? By counting the R groups. But all of these amines also have what in common? A lone pair of electrons. And that lone pair of electrons means that the nitrogen can behave as a nucleophile. And we've just shown that nucleophiles can add to carbonyl carbons, right? So what do you think the first step is going to be in an amine reacting with? There you go, right? And you're going to form a carbon-nitrogen bond instead of a carbon-carbon bond, okay? Just a different atom on the periodic table, but the mechanism's the same, okay? If you take an aldehyde or a ketone and you react it with a primary amine, you're going to get what's known as an imine. It's also known as a Schiff base, and it looks something like this. At that first level of knowledge that you need to know that aldehydes and ketones react with primary amines to give me imines, which are carbon-nitrogen double bonds. Basically, all you're doing is you're taking the carbon-oxygen double bond and you're replacing it with a carbon-nitrogen double bond. It's pretty sweet. Just switch the oxygen out for the nitrogen and you're done, right? Now, as Aubry said, he expects that the first step is going to be the nitrogen attacking the carbon of the carbonyl, breaking the weak pi bond, and what you get is what's known as a carbanolamine as an intermediate. We've got an oxygen carbon bond and a nitrogen carbon bond. Then we lose water. The OH and the hydrogen eliminate water to give me the carbon-nitrogen double bond, okay? Usually these reactions are done with a mild acid catalyst, just a drop or two of a little bit of acid. Para-toluene sulfonic acid is kind of a common one, but not much. You just need a little bit to kick the reaction off and eliminate the water, and you can get the imine, okay? So let's look at the mechanism. The first step is exactly as Aubry says it's going to be, nucleophilic attack. We get the alkoxide intermediate, but this is a what kind of base, strong or weak? Fairly strong. What kind of acid is this? Fairly strong, so we get a proton transfer, right? And you end up with a carbanolamine. Notice this is all reversible, by the way. Then what happens is this gets protonated by that little bit of mild acid that we have. Now we've got what looks like a good leaving group, right? That's going to look like water. The lone pair of electrons attack here, kick out the water. You end up with a protonated imine, which then gets deprotonated to give me my acid catalyst back, okay? And so we eliminate water at this stage. What drives the reaction to the right and what drives the reaction to the left? How can I, in other words, how can I drive the reaction to the right? To the right? I got to remove water, right? Because we're producing water as a product. So if I remove the water on the product side, Le Chatelier's principle tells me that I'll go to product. Now, if I want to go in the reverse, let's say Gabriella has an imine, but she doesn't want the imine, she wants the aldehyde out of it. How does she reverse that reaction? She adds it to a lot of water. She'll take the imine, throw it into something like a liter of water, add a little bit of acid, and it will go in the reverse direction. Again, we can use Le Chatelier's principle to our advantage here, okay? And so I made imines all the time when I was a graduate student, and we just simply distilled out the water, and we could drive the reaction all the way to the right. We were in the Schiff-base making business at the time, okay? Easy to make. Mix the components together, drive off the water, the reaction goes, okay? Doesn't get any more, well, phosphorus chemistry is maybe a little easier, but it's pretty straightforward. You just got to boil out the water, okay? This has practical importance for those of you in biology. Well, actually it has practical importance for all of us right now because it's exactly how we're seeing the slide. The chemistry of your eyes are dependent on imines, okay? So what does this look like that we just talked about making? Yeah, this comes from beta-carotene, okay? And so beta-carotene, you've got an enzyme that cuts beta-carotene in half, basically makes two aldehydes. And in your eyes, you have these rhodopsin thingies, okay, for lack of a better term. And this is how we see, okay? Now, what you can see, opsin is a protein that's connected to the nerve, and that sends the electrical impulse to your brain, okay? So opsin is this big protein. It's got a nitrogen on it that condenses to form an imine with that aldehyde made from beta-carotene, okay? But beta-carotene has this cis double bond. Are cis double bonds stable or unstable? They're relatively unstable. And they can isomerize to trans double bonds if they absorb a photon. So you can actually take a cis double bond, put it in a UV reactor, shine a bright light on it for a while, and it will become a trans double bond. You break the weak pi bond, it can then rotate, and then it gets reformed. But it takes energy to do that, because it takes energy to break bonds, right? Well, fortunately for us, there's enough conjugation in this that this can absorb visible light, or what we know as visible light, okay? And so what happens is, as a photon from this slide is hitting my rods, if you will, okay? It is taking the cis double bond and converting it to a trans double bond, and when that happens, it changes its structure, and it tugs on the protein. And when it tugs on the protein, it sends an electrical signal to my brain that says light. And my brain has this, this perception of what light is, right? So that's how this works. Now imagine if this happened. Do you think it's easy to go from a trans double bond back to a cis double bond? It is not. So, I'm born, my eyes open, and I see for a few milliseconds, and then I'm blind for the rest of my life. That's not very practical, right? Nor is it reality. Why can I continue to see? What did I say about this bond? Forming an imine is what? It is reversible. So I have enzymes that form the imine. I see the light. Well, that sounds weird, right? It gets converted to the trans double bond. My brain registers the light, right? And this no longer senses light. So what happens? We have a whole set of enzymes that reverse this process, that convert this back to the opsin with the free amine. This gets dispelled, and another molecule of the cis double bond gets condensed with that, and it's constantly being regenerated. Okay? That's why you have to continue to eat your carrots, because you need that to keep seeing. Okay? Now, I've oversimplified that. I'm sure my biology friends would cringe at what I've just described to you. But chemically, this is true. Okay? Chemically, this is true. And so your eyesight depends on the formation of shift bases and the fact that they're reversible. Okay? So you can see the light, so to speak. Okay? That's kind of cool, right? Now, that's with primary amines. So a primary amine plus an aldehyde or a ketone gives me an imine. If I have a secondary amine, I get a different product. A secondary amine plus an aldehyde or a ketone doesn't give me an imine, it gives me what's called an enamine. Can you tell me why we call this an enamine? What?
Well, the double bond's no longer on the nitrogen.
Okay. And what do we call carbon-carbon double bonds? Alkenes, right? So it's an alkene amine, so they call it an enamine. Okay? Now, it turns out that these enamines are very useful materials for doing a variety of things that we'll talk about in another chapter. But right now, you need to know that if I take a primary amine and an aldehyde or a ketone, I get a imine. If I take a aldehyde or a ketone and I react it with a secondary amine, I get a enamine. That's right. What do you think the first step of the reaction is going to be? Probably the same thing as before, right? It's going to attack the weak carbonyl, break the weak pi bond, I should say. So same kind of thing. You've got a carbonyl. You've got a secondary amine, mild acid. You get an enamine. Okay? In both cases. The mechanism is exactly as you would have predicted. First step is breaking the weak pi bond. Proton transfer, we get a carbanolamine, just like we did in... So this is exactly the same. Where things get different is that when this gets protonated, We now have a good leaving group. The nitrogen has a lone pair of electrons that come down. You get what kind of looks like an imine, except what? The nitrogen is not neutral anymore. It's positive. Does nitrogen like to remain positive? Not really. And we've got these hydrogens on the alpha carbon, which are acidic now because of this positive charge. And so water comes in and deprotonates this. We form the carbon-carbon double bond, and we have the nitrogen with its lone pair. Okay? This is where things get different in terms of the mechanism. What you need to remember is a primary amine plus an aldehyde gives me an imine. A secondary amine plus an aldehyde gives me an enamine. That's right. We've already talked about that, so I'm going to skip that, skip that, skip that, skip that, skip that, skip that. We're done with that. Almost. Enamine. We did those slides the other day. All right. I want to talk a little bit about some spectra stuff that we need to know about aldehydes and ketones. So we're going to skip through some of these fairly quickly today. So remember, going back to chapter, what was it, 2 or 3, when we talked about IR spectra, right? IR spectra are very important for aldehydes and ketones, right? They allow us to know what kind of functional group we have. As you might expect, an aldehyde or a ketone is going to give me an absorption somewhere between 1,500 and 2,000 because of the carbon-oxygen double bond. I expect that stretch to be strong. Why? Okay. Do I expect that stretch to be stronger or weaker than a carbon-carbon double bond? Stronger because of the electronegativity difference. So when I stretch a carbon-oxygen double bond, I change the dipole a lot. And IR spectra is all about changing dipole. If I stretch a carbon-carbon double bond, does the dipole change very much? It changes a little, but not a lot, right? And so when we see stretches like this around 1600, we know that we've got some kind of carbon-oxygen double bond in there, right? And so aldehydes typically show these peaks around 1700, and you also see the CH bond to the aldehyde somewhere around 2700, okay? So you can see those quite distinctly in the IR spectrum. We can also tell what type of ring we have in these types of cyclic ketones by our IR spectrum. So for example, if I gave Obri cyclohexanone, cyclopentanone, and cyclobutanone, and I said our NMR is broken, figure out for me which bottle contains what. He can do this by simply going over to the lab and putting a drop of each one on a different IR and getting a spectrum. Notice what happens to the absorption frequency. If it's a 6-membered ring, you'll see this at around 1715. If it's a 5-membered ring, you'll see it at about 1745. And if it's a 4-membered ring, you'll see it at about 1780. Explain that for me. Aren't they all just carbon-oxygen double bonds? It does. Now tell me why. Olivia, take it away. Why? What happens as we go from 1715 to 1780? Which way am I stepping? To the right or to the left? I'm stepping to the left. So it's all in that range for sp2 hybridization, but it's starting to move more and more towards what? Yeah, it's getting more towards like the sp region. It's nowhere near it, right? But what's happening is I change the shape or the geometry here. It's getting more and more kind of linear, right? Should that not shift it more and more towards that way? Absolutely. What would you predict for a 3-membered ring?
About 18, 20. So it went 30 from there, 35 from there, so I figure it's going to be a little bit more.
That's reasonable. That's reasonable. I mean, it's going to move to the left by about the amount you said, right? And that's what we would expect to see. Okay? So ring strain shifts the carbonyl absorption to the left. Okay? So on an exam, you could distinguish these if I gave you an IR spectrum. You'd look and you'd go, okay, that's probably going to be that one. It's been shifted a little more. Yes, ma'am.
What happens if it's like 1760? Like, do you just guesstimate like which way it's closer to?
Mhm.
So it's just whichever one it's closer to is going to be what?
That's a good assumption for you right now. Yep. Okay. But if you think about it, conjugation also has an effect. What does conjugation do to a carbon-oxygen double bond? It stabilizes it, right? And so we're going to see this in a predictable manner as well. We're going to go to lower wave number, okay, by about 30 for each time we have some conjugation. So if we look at this molecule and we look at our good friend acetophenone, what did conjugation do? Lowered it by about 30 wave numbers, right? And so if we stabilize that carbon-oxygen double bond, that's going to shift it to the right a little bit, lower the frequency. And that makes sense. It's more stable, right? So you can see that here as well. NMR spectra, I'm not going to show all of this. You can read that for yourself. But if you look at the spectrum for this molecule, we should see 3 distinct hydrogen regions, and we do, right? This is a triplet because it's got 2 neighbors. This looks like a quartet because it has these 3 neighbors. But wait a second, what about this? Isn't this a neighbor? Most certainly is, right? But the coupling constant for aldehydes is really, really small. So you usually don't see it very well unless you have a really good instrument. And so this, if you think about it, this should actually be split by these 2. It should look like a triplet, but it actually looks more like a singlet. If you hone in on it really, really carefully, you'll kind of see the triplet pattern emerge, okay? Carbon-13 spectra are as we would expect. We see this at about 200. We see these 2 about where they should be, right? This one being this one because it's closer to the oxygen than this one, right? So we see what we should see. Let's skip that. There are some interesting aldehydes and ketones that you should know a little something about just because it's interesting. Citral. Okay, we've got an aldehyde. It's conjugated. It's also got this other double bond out here that's not conjugated to the rest of it. Lemongrass. This is the odor of lemongrass. It is an aldehyde. This is cinnamaldehyde. This is the unoxidized version of the cinnamic acids and the cinnamates that I talked to you about earlier. This is what gives the odor of cinnamon. If you like potpourri and you put all this stuff together, the smells that you're smelling are aldehydes usually, or esters. But since we're talking about aldehydes here, right? Benzaldehyde. Almonds kind of have the smell similar to cherries, believe it or not. But I kind of, if you ever get a bottle of benzaldehyde in the lab and you smell it, you'll know because it does smell like a jar. Somebody's opened a jar of maraschino cherries. Okay. And then 2-heptanone, this is the odor of blue cheese. Okay? You hate blue cheese? Somebody opened this up around you, you'd probably go, ugh, right? But blue cheese has the odor that it has because of the 2-heptanone. Okay? We've talked about all that good stuff. We don't need to talk about that. We talked about that before. We talked about that. Here we go. Another nucleophile that we can add to carbonyl groups is cyanide. Not surprising, right? Cyanide's a good nucleophile. Carbon having a negative charge, it's going to attack the carbonyl, break the weak pi bond, and we end up with what's called a cyanohydrin. Cyanohydrin, okay? Or a cyanide alcohol, if you will, okay? You typically do these reactions in mild acid. You've got cyanide around, mild acid, you're really going to have HCN. So guess what? We're not going to have any of you do these chemistries, okay? Because hydrogen cyanide's, of course, very toxic. But the mechanism, the same as everything that we've talked about before. But the cool thing about this is that these cyanohydrins actually are reversible under certain conditions. So for example, if you take a cyanohydrin and you put it in concentrated base, it will actually liberate cyanide for you. And that turns out to be biologically important, and we'll talk about that in just a second. But also you can convert these cyanohydrins into alpha hydroxy carboxylic acids. How many of you have heard of alpha hydroxy anything before? Skincare products, maybe? Yep. This is how they make them. Okay? They hydrolyze cyanides to alpha hydroxy acids to make whatever they do in skincare products. Okay? They're useful for a variety of reasons. Now, amygdalin and linamarin, these are cyanohydrins that are, you don't have the hydrin really because there's not a hydrogen here, it's a sugar molecule, but amygdalin is actually present in apple seeds. How many of you ever heard that eating apple seeds can be toxic? It absolutely can be. They contain cyanide. When these things hit your stomach, they will hydrolyze into HCN gas. So, how many of you have ever eaten an apple and accidentally swallowed an apple seed? You're still here, right? Why is it that you're still here? You wouldn't actually need a bazillion of them. There's enough cyanide in a couple of apples probably to kill you. It turns out that the shell of the apple seed, your body can't process it. It's tough. As long as you don't take I don't know how many it take, 100 apple seeds or whatever, grind them up and eat them, yeah, it'll probably kill you. Okay, but so it's important. Okay, so you can actually liberate hydrogen cyanide through these processes.